Okay, so we're looking at this idea about valence electrons. And the reason why valence electrons are so important is because they are the ones that are going to either be given away or taken from another atom or shared in the process of bonding. And bonding is just the way atoms combine to form new compounds, such as water or salt or hydrochloric acid or all sorts of compounds. There's only like 92, 93 naturally occurring elements in the entire universe. All the others are man-made. But there are millions and millions, probably trillions of compounds that are formed from the combining of atoms. So the way I think about that is I always think about Legos, where Legos are put together to form new things. And if you think about the new Lego movie that came out recently, you know, that whole city was made of Legos, all the people are made of Legos. Everything in the entire universe is made of atoms. And so how they combine is going to form new products that are useful by the things that they're made. Sometimes they're harmful, sometimes they're useful. But atoms in their natural state, you know, in the periodic table, they typically are not found that way. They're not by themselves, they're not isolated. So they form these compounds to become stable, which means that they're not as harmful when they're by themselves. And so the way they do that is they try to gain or steal or share electrons to fill their outer ring, and that makes them stable and they don't blow up or go crazy a lot of times, depending on what they're making. Okay? So if you remember in our periodic table, there was a note that we made where atoms going from left to right become less reactive. So there's one particular group that is more reactive on the right-hand side, and that is group 17. And so as we go over this, we'll explain why group 17 is just as reactive as group 1. So it's kind of like the rule breaker of going from left to right. They are nonmetals, by the way, where group 1 are metals, with the exception of hydrogen. Okay, so we're going to be looking at, primarily we're going to look at row, or period 2, and period 3, and how those work. So our book kind of gets us started showing us this dot structure. Let me find a different marker that works better. Let's see here. I think I have a red one up here. So the dot structure, we talked about how atoms are made. And you can look at my other videos and go back and review about how atoms are made. On this YouTube video I'm making right now, I'll put a link right here that allows you to click on that link and go back and see how to draw the full atom. But right now we're going to talk about just the valence electrons. So lithium is in group 1. And remember, groups go down. He's also in period 2. Okay, so period 2 are the rows going left to right, groups are going down. Okay? So remember, period 2 tells me there's 2 rings in these atoms. So when we draw the nucleus, there's 2 rings, and we're only interested in the second ring, not the inside ring. Okay? So group 1 tells us something about those atoms. It tells us that there's only one valence electron in the outer ring. So to draw a dot structure, we just put a little dot to represent that it has one valence electron. Now, since it has 2 rings, that second ring can hold up to 8 electrons. So it's 7 short. That means that this atom is going to act very violently to try to either get rid of 1 or gain 7. Well, it's much easier to get rid of 1 electron than it is to gain 7. So if he can get rid of just that 1 electron, his inner ring becomes his outer ring, and it's full. So he becomes stable. So it kind of follows this pattern, and you'll see it, because Mendeleev recognized this. Mendeleev said, I'm going to create a periodic table that is showing the atoms by atomic mass. So he arranged them by atomic mass, but he also arranged them by their reactivity, the way they behaved and the patterns that he noticed in reactions. And so you're going to see this pattern show up very vividly as we go through this. So when we look at group 2 atoms, we're going to look at the very next one next to lithium, which is, beside lithium, is going to be beryllium, Be. Now he's in group 2. So group 2, remember, goes down. And that's going to tell me in the outer ring of beryllium, he doesn't have 1 valence electron. Guess how many he has? 2. So we're going to put 1 here and 1 here. So we're going to kind of go around like an orbit around this beryllium atom to show that these electrons are starting to fill the outer shell. Okay, now remember we had a rule that groups 12, you know, when we look at the periodic table, it kind of does this. Okay, so I always draw this a little bit wrong. It kind of goes like this because this is hydrogen. Then we have lithium and beryllium. And then next to beryllium we have boron, and so on. This is group 1, and it goes down. Group 2, that's group 2, goes down. And then we have groups 3 through 12. Now these are the transition metals that kind of form a rectangle in here. They do not follow the rule that we're talking about. So we normally draw a line through those so we don't use the rule that we're using today for those guys. But then we get over here to group 13 where boron is, and we ignore the 1. And so it would be 3 valence electrons for group 13. Okay? So just remember that when we're looking at our periodic table. We're really just looking at periods 2 and periods 3. Okay? So the next one over, because there's that big gap, where it drops out, so we have, these two, this row and then this row right here. So that gap kind of falls out. So now we have group 13. And it's going to be boron. Remember, we ignore the 1. So how many valence electrons should that one have?
3.
3. So we're going to go 1, 2, 3. Okay? Okay, then we have carbon right next to that in group 14. Okay, so how many is it going to have?
4.
I'm kind of riding uphill. I need to come back down. So it has 4. Remember that outer ring can hold 8 in period 2. Because it has 2 rings, so that second ring can hold up to 8. So we can keep filling that guy up. So next to carbon, we have this atom called nitrogen. It makes up 78% of the Earth's atmosphere. Okay, group 15. How many is it going to have?
5.
5. So we're going to go 1, 2, 3, 4, and 5. We're going to start adding 2 in those spots, okay? Then we have group 16. Group 16 is going to be oxygen. How many is it going to have?
6.
6. So 1, 2, 3, 4, 5, 6. Okay? Then we have group 17. And we have fluorine. How many is it going to have?
7.
7. So 1, 2, 3, 4, 5, 6, and 7. Okay, before we move to group 18, check this out. Lithium has 1. Fluorine has 7. Well, he would like to have how many in his outer ring?
8.
8. If he could have 8, he'd be really, really stable. So if lithium way over here can give to fluorine, he can give away his 1 electron over here, and these guys will form a bond. It's called an ionic bond, where this electron is given away to fluorine. Well, the problem with that is that fluorine has extra electrons at that point. That's called an anion, because he's more negative. Now, because lithium gave away an electron, he's got more protons than electrons. We can't forget those guys are still in there. And so he's more positive. And that ion is called what? Do y'all remember? What is it? I heard somebody say it. You know what?
A cation.
A cation. Good. So the way I remember, or try to get students to remember that, is when an atom becomes positively charged, it's a cation. So think of yourself in a jungle and you're, don't have any weapons to defend yourself, and there's a hungry lion. That cat is positively going to eat you. So a cation is positive. Okay, now then, we have group 18 atoms, which are the noble gases. Remember, they don't bond with anybody, and we're going to find out why they don't bond with anybody. So we're going to look at neon. How many should I put for him?
8.
8. And how many can the outer ring hold?
8.
8. See, he doesn't want to get any electrons, and he doesn't want to give any away. He's very greedy. He wants to keep what he has, which makes sense because he has everything he needs, so why give it away? And he doesn't want to take any either. So he's completely stable. He doesn't want to steal any from anybody, and he wants to be left alone. So neon will not even combine with himself. Okay? Now the one exception to the rule, we didn't do group period 1, which helium is right above him. And helium kind of is the weird oddball in group 18. He only has 2 electrons. But remember, how many electrons can be filled in the first ring?
2.
Only 2. So helium does belong in group 18, even though he doesn't have 8 electrons in the outer ring, he has 2. But remember, the inside ring can only handle 2 electrons. So if you kind of need to know a little more about that again, go back and look at the YouTube video that talks about how to draw the full atoms. Okay? Okay, now we're going to look at period 3. Now period 3 has 3 rings. And that third ring can hold 8 electrons as well. So we have sodium, Na. It's right below lithium. It's in group 1. So guess how many electrons he's going to have? 1. Okay, then we have right next to that, we have magnesium, Mg. Okay, he's in group 2. So guess how many electrons he'll have in the outer ring? 2. And we really need to start calling them valence electrons because we got to get used to that word. Okay, then we have group 13, aluminum, right below boron. How many valence electrons will he have?
3.
1, 2, 3. Then we have right below carbon in group 14, we have silicon. How many there?
4.
1, 2, 3, 4. Then in group 15, right below nitrogen is phosphorus. So what do we got for him? 5, 1, 2, 3, 4, 5. Everybody see the pattern?
Yeah.
Okay, then we have, next to that, we have sulfur in group 16. How many there? 6, 1, 2, 3, 4, 5, and 6. Then next to that, we have chlorine, Cl. Okay, 7, good. 1, 2, 3, 4, 5, 6, and 7. And then next to that is argon. How many there?
8.
8, also stable, right? Group noble gas. Okay, so if we notice, if we start grouping these like they are in the periodic table, we notice these are in a family or group, family and group, family and group. That's the reason why these atoms behave the way they do, is because they are similar in the way they react. Because they all want the same kind of electrons from other atoms. So they're going to behave in very much the similar way. Now they may be different colors. They may be, when we start getting across the periodic table, we start running into groups that have metals, nonmetals, and metalloids, right? One of those famous areas is group 11. Well, actually group 14 has some nonmetals. Group 15, 14, 15, and 16, and even 17 have a combination of metals, nonmetals, and metalloids. So even though they're kind of broken apart by what their types are, their reactions are very similar in the way they behave. Okay? All right, everybody cool on that?
Yeah.
Okay, sweet. Well, let's go back and take a look one real quickly again. If we have lithium and chlorine, for example, combined, we have lithium with 1 valence electron, and we have chlorine with 7. 1, 2, 3, 4, 5, 6, 7. Okay, see, these guys get together and they make a deal with each other. This guy says, hey, I want to get rid of my 1 electron. And he says, will you take him from me? So it jumps right over here. Now it's gone. Okay? Now this atom becomes happy because his inner ring is full. So he's stable. This guy becomes happy because he stole his electron. Now because he has an extra electron, he becomes negatively charged. He becomes an anion. I also have a video that talks about ions, which I'll also link at this point, and you guys can check that out if you want to as well. Okay, this guy has lost an electron, but his positive protons remain the same. So he has more protons than electrons now. He becomes positively charged. He becomes a cation. And this is called an ionic bond. And that makes them stable. So this is lithium chloride. Okay? And you don't have to know the names right now. You'll learn all those names in high school.